Hello and good day. This is Mr. Roberts coming at you with lecture 1.3, How Percentages Can Be Misleading. Now, if you look on Folio, you will find a blank copy of this lecture. So if you want to go ahead and pause the video to download or print off a blank copy of this lecture to work on as you watch the video, I encourage you to do so. So feel free to pause the video right now and go download or print a blank copy of this lecture to accompany or fill in as you watch the video. But without any further ado, we're going to go ahead and get started. So in the previous lecture, you were introduced to percentages and what percentages are and how to utilize them. The word percent directly translates to division by 100. If you think about it, the word per often implies division in mathematics, and cent implies 100. That's why, a penny is often called 1 cent, because it takes 100 pennies to equal a dollar, or a century is 100 years. So per cent directly translates to divide by 100. Now, we saw when you did relative change that these percentages can sometimes be a little bit misleading. So let's go ahead and look at this first example here. So suppose because of losses by his employer, Jimmy has agreed to a temporary 10% pay cut. Jimmy's boss promises to give Jimmy a 10% pay raise 6 months after the pay cut. Will the pay raise restore Jimmy's original salary? So if you get a 10% pay cut, then a 10% pay raise, upon first impression, you may think that you're going to break even. That's actually not the case. That's because percentages are relative. They're applied to a particular quantity. So if you have a pay cut, a 10% pay cut to be more specific, it's going to be a 10% reduction of whatever the salary was. Then when you get that 10% pay raise, it's going to be 10% applied to the new quantity, which will be lower. So in this problem, we actually don't know what Jimmy's salary is. So go ahead and make up a salary value. And it doesn't matter what you go with. You can make up anything you want. So I'm going to go ahead and just say his salary is $50,000. So we're going to go ahead and issue that first 10% pay cut. So in order to compute that, we learned that back in the last lecture. So you can view that as that's 50,000 minus 10%. So 10% is 0.10 of 50,000. And we go ahead and compute that. And that is going to come out to, pull my calculator out, $45,000. So if you get a 10% pay cut, you're getting a 10% reduction, which will knock you down to $45,000. Another way you can compute this, another way of thinking about it, is if you have a 10% pay cut, then that means you're going to be getting 90% of what you were at. So you can do that as 90,000, or sorry, 0.9 times 50,000, which is 45,000. So it's two different ways to tackle that. Either way you shake it, after a 10% pay cut, Jimmy's going to be at a new salary of $45,000. Now, here's the kicker. He's going to get that 10% pay raise. The catch, though, is a 10% pay raise applied to the $45,000. So he's going to have that $45,000 salary plus the 10% pay raise. But it's going to be 10% of the $45,000. So that will come out to $49,500. And we can already see that that is less money than what he started off with. Now, it doesn't matter what you made up. You could have made up a $50,000 salary, a $1 salary, or a $100,000 salary, or a $1 million salary. You do a 10% cut, then a 10% raise, you're going to end up lower than where you started. So the answer to the original question is will the pay raise restore Jimmy's original salary? The answer is no. But the next question is, what is the percent increase or decrease from his original salary? So it would actually be factually incorrect for us to say that Jimmy is going to be making $500 less than where he started, because that's assuming he started off at $50,000. We don't actually know what his original salary was. We made it up. Now, if you want to be 100% technically correct, you would introduce a variable here and manipulate that variable. But this tends to cause confusion unless you're very comfortable with algebra. So instead of using a variable, we just made up a number. But if we want to compute the actual percent change, we can use these numbers. So to compute the percent decrease, what we have to do is compute the relative decrease. So if in the last lecture you learned how to do relative decrease, it's going to be the same thing here. So let's go ahead and do that. So go ahead and insert an equation. And we're going to insert a fraction bar here. So in order to complete this, what we're going to have to do is compute the percent change. So essentially what that looks like is you're going to do 49,500 minus 50,000, right? Because his pay started at 50,000, he ended at 49.5. So you subtract those two, that's the percent change. Now notice it has gone down, so we should be getting a negative value. That's why we're doing the 49,500 minus the 50,000. And then you're going to always divide by the value you subtracted. So you go ahead and compute that. And that is going to equal negative 0.01, which is negative 1%. So that means if you get a 10% pay cut, then a 10% pay raise, your salary will be 1% lower than where you started actually. So you're not going to be breaking even, you're going to be operating at a loss. And you can kind of see the values there. Now what's cool about using the relative decrease here is it doesn't matter what dollar amount you use at the beginning, it will always come out to negative 1%. So whether it's a $50,000 salary or a $1 million salary, it's always going to come out to a 1% loss if you have a 10% cut than a 10% raise. So let's go ahead and look at another similar example. So suppose you got a stockbroker offers the following defense to angry investors. I admit that the value of your investments fell 60% during my first year on the job. This year, however, their value is increased by 75%, so you're now 15% ahead. Evaluate the stockbroker's defense and determine the actual percent change. So suppose you take a 60% hit. Your first year of investing is a huge loss, right? You lose 60% of the value. But then the next year, you have a 75% increase. Does that mean you're ahead? Well, let's go ahead and take a look at it. So what we're going to do here is just go ahead and make up an original value. So you can make up anything you want. I'm just going to go ahead and use $100. Again, you can make up whatever you want. I'll just use $100. Or let's say $1,000. We'll go with 1,000. Doesn't really matter. So what happened in the first year is it fell by 60%. So let's go ahead and do that. So your $1,000 went down by 60% of 1,000. So you go ahead and compute that. That's going to equal $400. Another way of doing that is you can just do 0.4 times 1,000. So there's the percent change. So if you were starting off at $1,000 and you have a 60% decrease, that's going to knock you down to $400. But then what the stockbroker is saying is, okay, it went down 60%, but then it increased by 75%. Well, that means our $400 then went up by 75%, which is 0.75. The problem is, at the time of that 75% increase, our value is down from where we started. It's down to $400. So you go ahead and compute this. So let's see what happens when you go up by 75%. And that's going to equal $700. So if you go down by 60%, then up by 75%, you're still going to be operating at a loss, actually, which is kind of surprising. You may not have suspected that. You thought, okay, well, maybe if I did a 60% decrease then a 75% increase, I'd at least be, operating at a profit. Actually, you'd still be at a loss. Now, we don't know the actual dollar amount of the investment value. We made up the $1,000. So if we want to compute the change, we have to compute it in terms of percentages. So for the percent change, let's go ahead and compute that. So let me get my fraction bar set up here. Okay. So we want to do the 700 minus the 1,000 because we're down $300. And remember, with the trick with percent change, anytime you're computing it, the number you subtracted is the number you divide by. You just want to make sure you get the order subtraction right. You don't want to do the 1,000 minus 700 because then you're getting a positive number indicating an increase. Notice it went down, so we should be getting a negative number. So you go ahead and compute this, and you will be getting negative 0.3, which is negative 30%. So again, pretty surprising there. If you take a 60% hit, then a 75% increase, you're still operating at a 30% loss. So negative 30%. So I would say that this stockbroker needs to be fired. He's not even remotely close to being accurate with what he's saying. It's not how percentages work. Or if you go down 60%, then up 75%, you can't just subtract them and say, okay, now you're ahead 15%. That's factually incorrect. You'd actually still be down by 30% from where you started. All right, let's go ahead and take a look at the next example. So suppose we got a basketball game, and we got two players here, Kevin and Kobe. We want to go ahead and complete the table and answer the question. So let's start by computing Kevin's shooting percent. So Kevin made 4 baskets out of 10 attempts. So 4 divided by 10 gives us a 40% success rate. And then let's go ahead and do it for Kobe. So Kobe made 1 out of 4, which comes out to 25%. And now let's go ahead and do the same thing over here. In the second half of the game, Kevin made 3 out of 4 baskets, which comes out to 75%. And Kobe made 7 out of 10, which will come out to 70%. So now that the table is complete, let's go ahead and answer the following questions. The first question asks, who had the higher shooting percentage in the first half? Well, in the first half of the game, Kevin made 40% of his baskets and Kobe made 25%. So Kevin has the better shooting percentage in the first half. The next question asks, well, who had a better shooting percentage in the second half? And we look at the percentages. In the second half of the game, Kevin was 75% accurate. Kobe was 70% accurate. So Kevin was the better shooter in the second half. So Kevin is the better shooter in the first half of the game. Kevin is also the better shooter in the second half of the game, which begs the question, who had the higher shooting percentage overall? And this is where you got to be careful with percentages. You might say, well, Kevin had the higher percentage in the first half and the second half, so if you're better in the first half and better in the second half, aren't you the better shooter overall? Well, not necessarily. What we need to go ahead and do here is compute the overall shooting percentage for both Kevin and Kobe. So let's go ahead and take a look at Kevin's. So we need to add up the total number of baskets. So for the entire game, Kevin made 7 baskets, 4 plus 3. He made 7 baskets, and he had 14 attempts. He had 10 attempts in the first half, 4 attempts in the second half. So he made 7 out of 14 shots. So that tells us 7 out of 14. His overall shooting percentage for the entire game is 50%. Now, if we look at Kobe, scrolling back up to the chart, Kobe made 8 baskets. He made 1 in the first half, 7 in the second half. So he made 8 baskets out of 14 attempts. He had 4 attempts in the first half, 10 attempts in the second half. So he made 8 out of 14. And if we take a look at that, 8 divided by 14 comes out to roughly, 0.5714, which is roughly 57.14%. So overall, Kobe had the better shooting percentage. So Kevin had the better shooting percentage in the first half and the better shooting percentage in the second half. But if you look at the entire game, Kobe actually had a higher shooting percentage. Now, this might be kind of surprising. You might be wondering, well, how can these percentages be so misleading? How is it that a certain player can be a better shooter in the first half and a better shooter in the second half, but not be a better shooter overall? Well, the reason for that is because there's not a uniform distribution of baskets and attempts across both halves of the game. If you look in the first half, Kevin had way more attempts than Kobe, but Kobe had way more attempts in the second half. So since there's not an equal distribution of attempts across the two halves, then you could have a situation like we see here. So let's go ahead and look at the next problem. So this data is a few years old. We got it from an old textbook. I'll actually say it's a little over 10 years old, but we'll go on and run with it. A mammogram is an X-ray procedure used to detect breast cancer. A positive mammogram is supposed to indicate a malignant tumor. The results of 10,000 mammograms are given in the table below. Use the data to answer the following questions. So the questions are asking, how many true positives are there, true negatives, false positives, false negatives. So let's go ahead and take a look at that. So a true positive means the patient tested positive and has a malignant tumor. So the whole idea is that if you test positive, that means that means the test is indicating you have a malignant tumor. So it's positive in that you tested positive. It's true in that the test is correct. So if we look at the table, there are 85 true positives, right? There are 85 patients who tested positive and have a malignant tumor. So if we go and take a look at the next one, what's a true negative? That means the patient tested negative and has a benign tumor. So it's called a true negative in that it's negative because the patient tested negative. It's true in that the negative test result is correct. And if we look at our table here, there are 8,415 people who tested negative and have a benign tumor. Now, in a perfect world, you would only have true positives and true negatives, right? In a perfect world, all the test results would be correct. But unfortunately, it's not perfect, right? Sometimes the test is wrong. Sometimes the diagnostic is incorrect. So you can have a situation with a false positive. So what this is, this indicates that someone tested positive when they should have ideally tested negative. In other words, they tested positive when they don't actually have a malignant tumor. So these are the people who the test indicates that they have a malignant tumor, but they don't actually have one. So if we look at our table, there's going to be 1,485 people who tested positive, right? They have a positive mammogram, but it's a benign tumor. So there's 1,485 false positives in this data set. And then if we go ahead and look at the false negative, this means that the patient tested negative, but it's false because they should have, in a perfect world, should have tested positive. So in a perfect world, they would have received the test result that reflects reality. In other words, these are the people who tested negative when they actually do have a malignant tumor. And this is probably the most dangerous situation because the patient goes in, they get tested, test comes back negative, so they think they're in the clear. They think they're safe. All right, cool, I tested negative. I do not have a malignant tumor. Everything's hunky-dory. When in fact the test was wrong and they do actually have a malignant tumor. So if we look at our table here, there's going to be 15 people that received a negative result but actually do have a tumor. The test missed it. The test was incorrect. So there'll be 15 false negatives here. All right, so let's go ahead and continue playing with this data a little bit. So the next question is, what percentage of malignant tumors were correctly identified? So let's go ahead and take a look at that. So there are 100 malignant tumors. So if you look at the totals, there were 100 malignant tumors, 9,900 benign tumors in this data set. So, out of those 100 malignant tumors, how many were correctly identified? Well, 85 of them tested positive. In a perfect world, all 100 would test positive, but it's not perfect. 85 out of 100 were correctly identified by the mammogram. So 85 out of 100, that equals 85%. So if you had a malignant tumor, there's an 85% chance that you test positive. Let's go ahead and look at this next one. What percentage of benign tumors were correctly identified? So let's look at all the benign tumors. There were 9,900 benign tumors. So out of those 9,900 benign tumors, how many were correctly identified? So you want to be careful here. If you have a benign tumor and the tests were perfect, all 9,900 people would test negative. Right? Negative mammogram is supposed to indicate, that there is not a malignant tumor. So that'd be 8415. So we go ahead and punch that in. So 8415 divided by 9,900 is 85%. Let me just go ahead and confirm that real quick. Yep, 85%. So that begs the question, how accurate are the mammograms? Well, there's two possible situations. Either you have a malignant tumor or a benign tumor. If you have a malignant tumor, there's an 85% chance it's going to get correctly identified, according to this data. If you have a benign tumor, then there's an 85% chance it's going to be correctly identified. So overall, it'd be factually correct to say that the mammogram is 85% accurate. Now, time for the million-dollar question. The whole point of the mammogram is you don't know if you have a malignant tumor or benign tumor. You don't know. So you go get tested, and suppose the doctor tells you, data indicates that the test is 85% accurate. You test positive. That begs the question, well, what's the probability your tumor is malignant? Well, you might think, well, 85%. Right? It's an 85% accurate test, so if I test positive, there's an 85% chance that I have a malignant tumor in this case. Well, you want to be careful here. You don't know if you're one of these 100 people with malignant tumors, but you do know that you tested positive. So you're one of these 1,570 people that tested positive. So let's go ahead and run the numbers real quick. So you're one of the 1,570 people that tested positive. And out of those 1,570 people that tested positive, again, the whole point of the test is you don't know if it's malignant or benign. You just know that you tested positive. Well, how many of those 1,570 people have a malignant tumor? The answer is only 85 of them. So you go ahead and compute that, 85 divided by 1570. And you get roughly, 0.0541, which is roughly a 5.41% probability. Which is, I would assume many would find this quite surprising. Like, how can the test be 85% accurate, but then it results in a 5% probability that if I test positive, it's malignant? Well, that's because the overwhelming majority of tumors are actually benign, thank goodness. So that introduces a huge skew in the data. So the test is 85% accurate. That means it's going to be wrong 15% of the time. So in the case of malignant tumors, it's going to be wrong 15% of the time. In the case of benign tumors, it's going to be wrong 15% of the time. The problem is 15% of 100 is a lot smaller than 15% of 9,900. Now, again, this isn't, anything, intentionally deceptive. This is just, how nature is. Most tumors are benign. So that percentage is going to create way more false positives than false negatives, right? Because you're doing 15% of a much larger number. So that's going to cause a huge skew in the probability. This is why you can have a test that's 85% accurate, but results in a 5% probability of actually having a malignant tumor. And this is well known, right? This isn't in the medical and scientific community. So there's actually a theorem in probability called Bayes' theorem that addresses this. You'll watch a short video on it. So this is very well known, and this is the reason why if you have a positive mammogram, you don't immediately get rolled into cancer treatment, which can be very expensive both in a monetary sense and a physical sense, perspective, a physical sense. Normally, if you test positive in a mammogram, you get tested again, or you have a biopsy, which is not treatment. It's still a diagnostic to figure out if you actually have a malignant tumor. That's because you would not want to roll someone into treatment, cancer treatment, on a 5% probability that they actually have cancer. Now, this isn't saying that the test is useless. The test isn't useless. The test is actually 85% accurate, but you have to address the mathematical reality that there can be a skew or a disparity between the test accuracy and the actual probability that the test is indicating what it's supposed to indicate. And that's, again, usually because there's a huge skew in the size of the two data sets. So let's go ahead and do one last example, kind of playing around with this. Kind of start off with a blank table here. So suppose you got a test for a disease that's 95% accurate for those who have the disease and 85% accurate for those who do not have the disease. So a lot of times these diagnostics will have different accuracy ratings under different conditions, whether environmental or other such reasons. Now in this case, a positive test result is supposed to indicate that the patient has the disease. Suppose within a sample of 4,000 patients, 2% actually have the disease. Complete the table and answer the questions. So in this case, we know the actual infection rate. 2% of people have the disease. Now, in reality, trying to figure out this infection rate with precision is almost impossible. It's very, very difficult to do in reality. But suppose we actually know it in this situation. So 2% of people have the disease. So 2% is 0.02 of those 4,000 people have the disease. So 2% of those 4,000 people comes out to 80. So that tells me that there's 80 people that have the disease. And then if there's 80 people that have the disease, well, that means all I got to do is just do a little bit of subtraction to figure out how many don't have the disease. So 4,000 minus 80 is going to be 3,920. So if there's 80 people that have the disease, that means there's 3,920 people that do not have the disease. So now that we have these two values figured out, and just to kind of clean up the table, let me go ahead and delete this part and this part. So we got those two things figured out. So now we can use these numbers to figure out the test results. So in the case of someone having the disease, the test is 95% accurate. So that means 95% of these 80 people are going to get the test they should get. Now, if you have the disease, you should test positive. In a perfect world, if the tests were perfect, all 80 people would test positive. But it's not perfect. It's 95% accurate. So 95% of those 80 people will test positive. So 95% times 80 is going to be 76. So there's going to be 76 people that test positive. Well, that means that there's only going to be 4 people that test negative. All you got to do is do a little bit of subtraction, right? If there's 80 people that have the disease, they get tested. Test is 95% accurate, so 95% of them are going to test positive. So that means 76 people will test positive. That means there's 4 people left over who tested negative. And we're going to do the same thing over here. Now we got to be a little bit careful here. In this case, it is 85% accurate for people who do not have the disease. So it's going to be a different percentage. Now, it would be incorrect to apply the 85% for testing positive under this situation. In a perfect world, all 3,920 people here would test negative because they do not have the disease. In a perfect world, they would all test negative. But it's not perfect. It's only 85% accurate in this case. So let's go ahead and run with that. It's 85% accurate, or 0.85. So 85% times 3,920. Let's see what that equals. Grab the calculator real quick. That's 3,332. So that means not everybody's going to test negative in this situation. In a perfect world, they would, but it's not perfect. Only 85% of them are going to test negative. So then you can just do a little bit of subtraction to figure out how many test positive. So just do 3,920 minus the 3,332, and we get 588. And then we can go ahead and figure out the totals. So just do some addition. So there's 76 people with the disease that tested positive, 588 people with no disease that tested positive. So if we add those two together, we can figure out that there were a total of 664 people that tested positive. And then we can do the same total down here. That'll be 3,336 people that tested negative. Again, just adding up across the row. So there we have it. Our table is complete. So we can go ahead and answer the questions now. How many true positives are there? So true positive means they have the disease and tested positive. So that would be 76. And let's go ahead and answer the next couple of questions. So the next question asks, of those who with the disease, what percentage test negative? So of those with the disease, so there's 80 people that have the disease. Out of those 80 people, how many tested negative? Well, there's 4 of those people that tested negative. So 4 divided by 80 is going to equal 0.05, which is 5%. So 5% of them will test negative. Now, you might think, if I flip that around, won't I get the same percentage? And you will not. You don't want to fall for the fallacy of the converse here. Of those with the disease, what percentage test negative? That'd be 5%. Of those who test negative, what percentage have the disease? Let's take a look at that. So now we're looking at all the people that tested negative. So if we look at our table, There's 3,336 people that tested negative. Out of those 3,000 plus people that tested negative, only 4 of them actually have the disease. So this is going to be a very, very small number. So 4 divided by 3,336. That's going to come out to 0.0012, roughly speaking. It's rounded. So that would come out to roughly 0.12%. So less than 0.5%. So very, very, very small people who test negative actually have the disease. And our last question for this lecture. Suppose a patient tests positive. What is the percent chance they actually have the disease? So they tested positive. So that means they are one of these 664 people that tested positive. So there's 664 people that test positive. And then what's the chances they have the disease? Well, to have the disease, they got to be one of the people that have the disease and tested positive. So there's 664 people that tested positive. They'd have to be one of these 76 people. So it's to be 76 out of 664 would be the probability. Let me double check. It said 76, right? Yep, 76. So the question is, what's the probability? So 76 divided by 664 comes out to roughly 0.1145, which is roughly 11.45%. So if you have the disease, the test is 95% accurate. It's 85% accurate if you don't have the disease. So you might be thinking, okay, well, if I test positive, then it's an 85 to 95% chance I have the disease. It's actually not true. It's closer to 11%. Again, substantially lower. Essentially, if you test positive under these circumstances, the next thing you'd probably want to do is test again. You would actually want to have multiple independent test results to confirm if you actually have the disease. You'd want more diagnostics. But that is it for this lecture. So I've covered everything that's in homework 1.3, so feel free to get started on that. And if you have any questions, feel free to shoot me an email. Other than that, have a wonderful day.